for what is probably interesting is, of course, that Professor Balbus is an expert in astrophysical fluid dynamics and is most, I think, well known for the magnetorotational instability. And he will be the main person today. And for us, for all of you, the event is really meant to be to give you a sharing by an international top scientist and to basically ask him about his kind of personal side, his journey, just so that you can kind of draw inspiration from this in your own journey ahead. Let's do some Q&A. I'll team tag Sonia in. Sonia, go ahead.
Okay, so good morning or good evening, Professor Balbus. Okay, good afternoon. So I'm Sonia from the Chinese University of Hong Kong, and I'm also Johnny's student. And I'm now an undergraduate, and so I'm still in a very early stage of my research career. So I have a question, so how do you select research topics, and how do you build up your taste for studying physics? So so when you approach a question, so how do you tell that this part of the question is worth studying, and how do you tell things that are probably not that meaningful?
Well, that's a very good question, and there's of course no right way and no wrong way to do something like that, because problems that you think look kind of straightforward then turn out to be much more complicated than you thought, and then other problems that look at first sight hopelessly difficult, when you turn around and look at them in the other way, they sort of fall into place. In my own experience, it's a combination of things. I started out, I knew I was interested in astronomy and astrophysics kind of from a very young age. I was old enough, or I am old enough now to have been a young boy at the time when the space program in the US was first getting started. So that was very exciting, and it was I didn't distinguish between sort of astronauts and astronomers then. It all just seemed to be a very exciting field. And then, by the time I was at university, I enjoyed doing mathematics and physics, just sort of who I was. And so it was kind of natural to combine all those interests and go into astrophysics for my graduate work. And I simply, I started off talking to my instructors about different problems that they had to offer. So in some sense, my choice was kind of initially provided for me. And it's interesting because the sort of work I did on my PhD was an area that I worked really just around the time of my graduate studies, and not really too long afterwards. I guess the advice that I can give more generally in something like that is that you should engage as much as you can with interesting visitors and interesting speakers, and to sort of listen to their talks, be aggressive, in a nice sense, of course, in the sense of not being shy, and follow up with further questions as to what they're doing, because you'll find that there are kind of interesting problems that you hadn't thought of and weren't aware of until somebody comes along and explains a new field to you. And then it's simply a matter of following your heart, to look at problems that sound interesting in their own right. There's no substitute, I think, from just talking and interacting with with your instructors, and especially with visitors, because that's very refreshing and very stimulating. If you have an active mind, as I'm sure you know that all of you have, or you wouldn't be in the field, what you find when you go through your work and you go through different topics is that one thing very quickly leads to another. There's aspects of a problem that touch on something else that you would not have seen had you sort of not begun with the first problem to begin with, and that can take you into different directions as well. For example, let me give you something very specific, and then I don't want to go on too long with this question, but I was very interested at one point in my career about thermal instability, how gases, when they're heated and cooled, that tends to be an unstable process. Cooling gases tend to condense and they cool more rapidly. And it's simple at first when you sort of look at the actual equations, and then it gets to be more complicated. And as I was working in that field, I came across a paper that treated the same problem of heating and cooling of gas, but with a magnetic field present. And so I read those papers, supposedly about heating and cooling, but I was just fascinated about what the magnetic field was doing there, because it was very counterintuitive. It wasn't at all what I had expected. And then later, when I started to look at the problems of accretion, I was in a very unusual situation because I had done what looked like a completely unrelated problem with thermal physics, but the magnetic field played such a strange role there that I thought, I wonder what happens if I introduce a magnetic field into this accretion problem. And really that was the beginning of, the work that I eventually got the Shaw Prize for. And it was almost a random kind of correlation, or I should say a random kind of connection. So that's a very long answer to your question. Executive summary: talk to lots of people, follow your heart, work on problems that are of interest to you, not problems that you think are going to be important for this purpose or some other purpose, but what really interests you, because those are the ones that you'll learn the best and you'll learn the most deeply, and that will then serve you well in whatever you do. I'll stop there.
Brilliant. Okay.
Thank you.
I think we can pick this up if there's time, but I want to first give everyone a shot, and then we can see if we need any topics that we want to continue discussing. So let me call forward then the next person. So I'm randomly selecting here, but it's Jern Ho Wang.
Hello.
Hello.
Could you hear? I have a few questions. I'm Garfield from HKBU, and I'm studying applied physics in BU as the year 4 student. And my question is, what is the purpose for us to study the beginning of our universe? Besides interest, besides we know we can generate some technology and then apply this some theory we learned from studying the beginning of the universe to our daily life. Or besides of all of them, what is the purpose to do that?
Well, there's no one purpose, of course. I would say you've touched on several aspects, and that's a very interesting question because there are just a huge number of very important reasons why that's a very, very important and interesting problem. And I'm not even going to touch on sort of the philosophical aspect of that in terms of our beginnings, what was, where do we come from? This is a question that many cultures throughout all history have been fascinated with, and everybody has their own. Most of the time, of course, it was a religious approach to the problem of some god or gods creating the universe. So let me just, to answer your questions, sort of stick to kind of the practical side. So the first thing I would mention is that the beginning of the universe is a physical environment which is extraordinary, and it can't be kind of studied in the laboratory. And so one of the most important reasons for doing it from a physics point of view is that it will teach us something very fundamental about the laws of physics that we can't get any other way. So for example, when you solve the standard quantum mechanics equations, everything is a wave. And we have waves going here and there, and particles are waves, and particles in our wave equations do nice, how shall I put it, wavy things. Well, in the early universe, we have quantum mechanical processes going on, but we now think that for a period of time, it wasn't very wavy. It was more exponential. So we can learn about a very unusual aspect of fundamental quantum mechanical fields in terms of the early universe, where conditions were such that the kind of interactions that were present didn't produce particles with normal mass, but produced particles, if that's the word for it, that kind of grew exponentially. So that whole area of study of inflation is something that began because there were a number of puzzles associated with the beginning of the universe. Another reason for doing it is simply that there is, as you say, enormous sort of technological interest in aspects of this problem. For example, one of the things that we want to do is, when we study the early universe, is to look at the universe looked at the time of recombination, when the atoms recombine to form, or rather when the electrons and protons recombine to form hydrogen, because by looking at the fluctuations of that background, we can learn something about very even earlier conditions in the universe. It's one of these subtle things, in the same way that archaeologists can or geologists can look at ancient rocks and reconstruct their history from just the kind of faintest of clues. By looking at the cosmic microwave background and what kind of noise is present, we can reconstruct what kind of universe we had earlier. But in order to do that, you need to get accuracies which are just fantastic. 1 part in 100,000, 1 part in a million. And the technology that you need to develop the millimeter receivers, which are responsible for actually doing the measurements themselves, things like in the Planck satellite and the WMAP satellite, that indeed was a huge technology spur just on its own, irrespective of the interesting science that results. And then finally, it's kind of foundational to the whole field of astronomy. By looking at how structure forms and how it evolves. The universe is very interesting, in case you haven't noticed. It's very finely tuned in that everything is expanding, and at the same time, we still have enough time for stuff to stop expanding and to fall back in on itself and make structures like galaxies, and clusters of galaxies, and then on smaller scales. So to have everything going out but still kind of gravitationally collapsing, that doesn't happen if you just sort of wrote down model universes. They'd either all collapse into a black hole, or they'd go on expanding and just be a boring expanding bunch of gas, and there wouldn't be any stuff falling back in. But our universe isn't like that. And so to understand why that is not only fascinating in its own right, but we sort of need to do that so that we can understand, well, what's in the voids between galaxies? What might have happened to magnetic fields? Where did the magnetic fields come from? All of these things touch on that problem. In some ways, understanding the origin of the universe, it's really, and I think many people would say it's the most interesting problem in theoretical astrophysics, both in its own right and because of the way it touches on so many other areas.
Okay, brilliant. Anya, can I ask a question?
So I'm Anya, I'm first year PhD student. So I'm Johnny's student at CUHK in Hong Kong. And I actually at first wanted to ask a similar question to Sonia about choosing the career path. So I thought I would follow up on that and would ask, is it difficult to balance out the scientific career as an academic with your private life? Because I know your wife is also an academic professor. I did my bachelor's at Oxford. I had lectures with her. So
very good.
I can imagine it must be a bit challenging, probably, to balance it. So I wanted to ask about your experience, about your thoughts on that.
Well, yeah, I think it's true. It's not the kind of job that you can sort of easily kind of leave at work. You know, you come home and there are lots of things, you know, that are on your mind. Well, the things that are on your mind. So you're sort of thinking about them when you're sitting at the table. That kind of goes with the territory. You're the classic example of an absent-minded professor. There's truth in that. It's not easy from that point of view. It helps, I think in our case, my wife Carolyn and I, we have a son who's very interested just in academic matters as well. So that makes family life kind of continuous. But not all of our children, our daughter, you know, wasn't like that. And so, you know, it is true that you have to make an effort. And for the first time in my life, I think as a student, I always was somewhat disorganized. I did things at the last minute, or like everybody, I procrastinated a little bit too much and then would try and get things done. When you are at a stage in life where you have to manage both kind of a pretty demanding professional schedule and you still want to be, you know, good parents, then there's no question that you have to absolutely put time aside to be with the family, to spend weekends, and, you know, to engage with them. And I think at this point, we've been pretty successful as far as that goes. In terms of, you know, I mean, I'm lucky for many reasons to be married to Carolyn. But one of the aspects of it that's nice is that we certainly both understand when the other is sort of locked in the room trying to grade a pile of papers. We're not going to demand that they spend more time with us. We understand exactly what they're going through. So, you know, I don't know whether that's an argument, you know, to marry somebody in the field or not, but I think the most important thing probably is to be aware of it and, you know, to be with someone who's understanding, like, you know, not just, I mean, this would be true, I would think, in any kind of a job, which would be very demanding. An important physician at a hospital will have demands on their time as well. And so that's exactly the kind of flexibility that you have to allow one another. So I feel like I'm sort of now a family counselor as well as an astronomer.
Just out of curiosity, do you ever discuss physics problems, or do you have arguments on that at home?
Oh, yes. Not terrible arguments, but no, yeah. If one of us thinks the other isn't looking at the problem the right way, then we definitely go back and forth. And actually that's good, because we learn from one another that way. We come back the next day and say, remember you were saying that, you know, it actually goes this way. I think you were right, yeah.
Okay, thank you very much.
Excellent. Okay, let's see if we could go back to Chen Kai-hei.
So hi, I'm Chen Kai-hei, and I had my undergraduate degree in HKU, and right now I'm an MPhil in CUHK. And so my question is, so I have been an astronomy student and doing research for, I think, like 4 years already. And I've always think about my career. I always want to be a professor or even a lecturer, so that I enjoy the stable, so-called stable salary, and I can enjoy the environment in schools. I can teach the future students, and I also have support, financial and also other stuff, maybe connection support in schools. So it will be a win-win situations. But I have heard that among many PhD graduates all over the world, there is only a few percent that they finally get the job positions to be a professor or to be a lecturer in the university. So is it the same case in UK or in Europe? And if that is the case, so is there any career that you would suggest astronomy student to chase for? So like what kind of jobs can they look for?
Well, that's a good question, and it is true that I think everywhere, not just in Hong Kong and China, but in Europe, the UK, and the US, the actual number of faculty positions, is indeed very limited, and so when you go into the field, if your only goal is to have a professorship somewhere, then the odds are pretty tough, and you have to sort of go into it with that understanding. But there are just a huge number of interesting and different career opportunities that someone who's been trained in astronomy or in astrophysics, has available to them. Kind of critical thinking skills and this sort of technical background that you have, whatever you do, the comfort that you have in working with sort of complex software, which even a very theoretical person these days is dealing with a computer and complicated codes for a large part of their research career. If you go into any kind of field, for example, I know a lot of people who have gone into financial analysis, which is very rewarding, of course, financially, but also is interesting from the point of view of working with kind of messy quantitative models, which is exactly what is the kind of training that astronomy gives you. There are also these days, much more than in the past, there are very large projects that require project scientists. And so many people, although they're not a professor at a university, have essentially long-term employment working in different national laboratories or working with a very long-term major projects like LIGO, like LSST, the Rubin Observatory. There are many, astronomy has become so, it's like particle physics in the sense there are these huge instruments that require people at all different kinds of level for support. And they are always looking for new people to come in and fill positions in that kind of a field as well. And then if you like teaching, there are professorships, and there are also, I'm finding now more and more that there are high school PhD teachers who, in the UK, it's been interesting because they're actually much more actively involved with professors and engaging with them. And even, you know, they have the advantage of working with good students and sort of directing them. And that is certainly, you know, a field where talented people are not only needed, it's really crucial that we be able to reach the students. I know it's interesting to me because in other fields, for example, the humanities, and I can see this in my own children's education, they have absolutely, you know, outstanding people engaging the high school level students in these fields. And somehow that's not within physics, it's not as popular a route, perhaps because in fact there are other options besides teaching. See, in the humanities you have really no other options. If you're a Greek scholar, you either have to be at a university, but it's not something that easily lends itself to another area of study. And so you get excellent people teaching high school. But in physics, there are other opportunities, but I would like to see more PhDs engaging with younger people, especially in the best high schools, where we really need to encourage them. We're kind of facing a future right now where we need more physicists. When you look at what's happening, for example, with climate, that's a very complicated problem. And what does it involve? It involves heating and cooling and fluids and complicated mathematics with turbulence in the atmosphere and convection. And we literally, you know, it has become a matter of life and death to have the best people thinking about the way forward on that. So if we can encourage young people from an early age to get interested in that, not only from the point of view of something necessary, you know, to save us, but just from the scientific side as well, that would be an excellent service. Okay,
I think we can switch gears a little. There are a few students from the high school level that
very good.
Have questions. So I'm going to call one forward. Let's see, Kwok Sum Yut, Keisha?
Yeah, hi, I'm Keisha, as mentioned. Hi, Professor Balbus. I have a question about what field.
I like your backdrop, by the way. That's very neat. Looks like
thanks.
The Milky Way plane. Go ahead.
Yeah, so I have a question. So basically, I recently ran across things like the Webb telescope and such telescope that will have the potential to dive into the ancient side of the universe. So I'm interested, first of all, what that will mean for us, and secondly, if I want to study such aspects in the future, what specific fields should I dive into in university?
Excellent question. So, yes, these are telescopes that are going to look at very, very distant times in the past. And astronomers will always speak of it in terms of redshift, at high redshift. And that's because distant things are essentially moving away from us. And so the signals that we receive have been shifted to the red part of the spectrum toward longer wavelengths. So these will look at the so-called high redshift universe. Well, at this stage in your career, you can't learn too much physics. So you absolutely should learn as much physics and mathematics as you can. So I wouldn't look for something very specific at this stage in terms of what will I need to learn so that I can know what star formation in distant galaxies looks like. Don't think of it that way. The best astrophysicists are the ones that have a general and very strong background in all aspects of physics, so that they can be comfortable with the technical way that the instruments work, as well as the science of the objects that are being studied. So my advice, especially to someone at your age, would to be to be as general as possible as you can with your course selections. Don't think of being an astrophysicist yet. It's fine to like it and it's fine to pursue it, but think of yourself now as a physicist who will look at astrophysics later in their career.
Okay, thank you for your answer. I actually have another question about a different topic. May I ask it as well? Sure.
If the moderator says okay, thumbs up from Johnny, so please go ahead.
Okay, so I read the Science Daily News and it said that the Australian SKA Pathfinder found a radio source like 2 years ago, which is like highly circular polarized and have extraordinary features. So they say there's this possibility that it's a new class called like radio transients. So my question is that what it means to have a new class of objects like that?
That's a difficult question. So that happens, I wouldn't say a lot, but it happens on occasion in astronomy and astrophysics, and it's always very important. So the classical example for that was the discovery of pulsars, where they found radio signals which were incredibly regular. And there's just no natural way they thought that something like that could happen. There was even speculation at the time it was evidence for extraterrestrial civilizations, but no, it turned out to be objects that had been thought of before in a very theoretical context, neutron stars, that were now manifesting in a very practical way by having their rapid rotation somehow controlling very regular pulses. So yes, these kinds of interesting, especially radio astronomy seems to be the area where we pick up on these a lot, because the radio astronomy is the area where you're seeing a lot of high energy particles, usually interacting with a strong magnetic field. And that always is an indication of something kind of neat going on. So the answer to your question is that the meaning of something like this is very hard to know in advance, but almost inevitably, it's something very important, something that hasn't been anticipated, or if it has been anticipated, has been kind of a sidelight. So to see that kind of degree of circular polarization, in a source means that you're probably dealing with something with a very strong magnetic field and very energetic particles. So is it a kind of neutron star or something beyond where, we have a standard theory? It's hard to say, but I would bet a lot of money that it will turn out to be something important.
Okay, let's have Krish, who had some connection problems before, but is now ready to ask his question.
Hello, Professor Balbus. First of all, it's an honor to meet you. I have a more general question that has to do with scientific investigation in general, which will be one of a few questions I'd like to ask. Hopefully, I could be able to ask all of them later. But first of all, because in science we would have to stay curious, right? So whenever I see different things, I would always be asking the question, why? Yet when sometimes as you continue to ask the question why forward and forward, and it starts to become more and more difficult until you reach a stop where it's almost impossible to explain it. Maybe it's because I haven't learned that yet, but to me it just sounds like you can ask why forever and forever. So for example, I could ask, why do we fall? So the answer would be because there's gravity. And I could ask, why is there gravity? The answer might be because any objects with mass could bend space-time. But if I continue to ask why again, why would an object with mass bend space-time? I become speechless, and I'd like to know what is your thought on that, and is my approach wrong? And yeah, that's basically it.
So your question is not on the specifics of why mass bends space-time.
Yeah.
question is on the method of continuously asking why and how productive is that. So the answer there is, I would say, is kind of a commonsensical one. That is to say, it is certainly of interest to ask yourself something which has been taken for granted and ask why. That is often the way that science is at its most productive. Why is there action at a distance in Newtonian theory? That was a perfectly good question to ask, and led, among other consequences, to the entire kind of modern concept of field theory and general relativity. So the initial stages of the why program are very good. It's not particularly helpful to, right from the start, have 10 levels of why, for exactly the same reason that it wouldn't be a very good program when you're doing something complicated like trying to figure out the weather, to try and use that to predict the weather a year in advance. The problem is that things are kind of fuzzy in the why world. And to go one step or two step, you kind of know your way. Beyond that, it's almost pointless, because you may have taken a wrong turn way back and what you're doing makes no sense at all. So while the why question is a very good one, I would say you should apply it sparingly, but when you do apply it rigorously.
So by what you mean, do you mean that sometimes there are things in the universe that really has no reason behind it?
Well, I don't know. You have to define what you mean by reason. There's always an explanation, I think. Now, there are different logical possibilities. You could imagine an infinite chain. Well, the reason for A is B, and the reason for B is C. The reason for C is D, going on and on and on and on. Or you could imagine a chain that comes to an end. The reason for A is B, the reason for B is C, and the reason for D is E, and E is the end. And somehow that is the ultimate. A religious person might invoke God at this point, but I'm not going to go there. But at least it's a logical possibility that the chain of command has come to an end. And then the third possibility is like a convergence of a sequence. The reason for A is B, and then you take that a little bit farther. The reason for B is C, but C is kind of close to B. And then when you take it another step, you can see you're kind of zeroing in on something and kind of getting closer and closer and closer to something which is ultimate, but never quite reaching it. It's like an asymptotic limit point. And from my philosophical point of view, I sort of suspect the real universe is going to turn out to be like that. That we won't always be looking at sort of layer after layer of whole new worlds, but we won't ever quite approach everything, but we'll get closer and closer and closer.
I think I get what you mean. So theoretically, for the first few layers, I would be able to ask why and answer it. But at some point in the sequence, I may be either entering a loop or...
Well, exactly. But also the why sort of question depends upon, where you've gotten it. It would not have been very fruitful for the Egyptians to try and think and ask the question, why is the dome of the universe shaped like a dome? That would be a question that they would say would be perfectly natural. We know now that's a completely ridiculous question. And the problem is that you're always in that situation if you go too far. The way that you frame the question may have nothing to do with the reality. if the Egyptians had said, well, the sky looks like a dome, I wonder why that is. What's going on? That would have been a good question to ask. But to think about who's holding up the dome and so on and so forth, that wouldn't have been very productive. So the reason is that you're going too far into the dark if you go too many layers too soon.
Okay, in the interest of time, let's see if we can pick this up later if there's time, but I would like to also give the floor to Lam Zeka.
I'm Lam Zeka, a current Form 4 student from SKHB's Masterminds Secondary School, and today I have a question for you. Is it possible for us to calculate the future of the universe, or is it possible for us to acknowledge every single information in the universe?
Definitely not. No, the interesting question. We cannot calculate that now. And then the interesting question is that in principle something that could be done by some kind of a superhuman computer or genius? So there was a time when that question was thought to be yes, that in principle, although the problem is horrendously complicated, in principle, if you could tell me where every kind of atom in the universe was at this point of time, I could use the equations of motion to predict the universe. And Laplace is the name that was associated with that kind of what they call determinism. But our understanding now of physics is much more subtle. And we know that we live in a quantum mechanical world where things happen through the evolution of wave-like quantities and operators, and that measurement influences the future and what actually happens. And in that kind of a world, it's very difficult to imagine, even in principle, someone being able to come up with some kind of a supercomputer that could predict the future of the universe. It's not really possible now even to predict the future of a very simple system. All we can tell you is various probabilities of what will happen in the future, and what, if you do a measurement, the probability of finding it in state A is this number, the probability of finding it in state B is the other number, but there's no way forward in terms of predicting a future which will then come to pass.
So is it we can know the possibility that a thing will happen, but it's impossible for us to know something very precisely?
That is certainly true, yes. The sort of level of complexity that's actually involved is so kind of enormously, how shall I put it, unstable, the tiny uncertainties. The universe is chaotic in that sense, in that infinitesimal different initial conditions can lead to completely different outcomes. So at all levels, it's essentially an impossible task.
Okay, thank you for answering me my question.
You're welcome.
Okay, so as the moderator, I'm also taking the liberty of throwing a discussion point in the group. For me, actually, and I'd be very curious to hear what Professor Balbus thinks, is where do you see the kind of the major discoveries within astronomy, let's say 5 years from now, 10 years from now, maybe 50 years from now? What do the various levels of students that are sitting here have to look forward to?
Oh boy, that's a big question. So I'm not even going to go 50 years. That's I can't imagine someone in 1920 predicting what the world of astronomy would be like in 1970. The areas where we're finding out all kinds of amazing things, and where I expect there to be lots of development are, I think we touched on it earlier. So one, sort of the traditional field of radio astronomy is getting better and better and better, and they're having better and better instrumentation. And the radio telescopes and radio receivers just probe a part of the spectrum which tells us about the most unusual forms of matter. And so I think we almost certainly haven't discovered all kinds of sort of objects, fundamental objects that are really out there. And even, within sort of the field of, say, neutron stars, there are different kinds of neutron stars. There are stars that are kind of just held together with gravity. There are neutron stars that are put together with magnetic fields that are so strong they're barely contained at the surface. And all kinds of interesting physics is going to come out of that. We'll be able to look at, for example, magnetic fields that are so strong that effects of quantum electrodynamics will be important. The vacuum will start to break down. And that's very hard. You can't do that in a laboratory. That's an astrophysical fundamental problem. There is the field you work in, Johnny, gravitational radiation. I don't need to tell you that has opened up all kinds of fascinating problems just in its own right within the field of gravitational radiation, but also just as a diagnostic tool for learning about other objects, looking at two merging neutron stars and putting together everything that happens and everything that we learn from both the gravitational radiation and the electromagnetic radiation. Probably one of the best ways to understand what the equation of state is for a neutron star, which is a very important question because that'll tell us how big neutron stars can be. When neutron stars collide, do they have a soft equation of state so that everything kind of falls quickly into a black hole? Or do they have a stiffer equation of state so that there's a huge amount that's ejected in the process? That will teach us where the elements came from. We thought we knew where the elements came from. Well, we know where some of them come from. We're not so sure now about the others. And seeing them form in these kinds of collisions, that's a whole new area of science. Cosmology is already starting to have, there was one revolution when we learned that, the last chapter in your astronomy book that you never really did read, that was the one that had the cosmological constant, but that was for the crazy people. So you'd read up through chapter 15, but not chapter 16. That, you had other things to do. Well, you should have read chapter 16 because there is a cosmological. So what is the cosmological constant? Is it what, the simplest explanation would be that in the vacuum itself, there's a finite energy density. Well, that makes predictions about how in detail the universe will expand. Is the real universe following that? Well, we have to see. That is certainly a question that will be addressed in the next 10 to 20 years. There is the whole problem about dark matter. So there just seems to be no question that it's there. All kinds of totally independent threads lead to the same conclusion. And we need the particle theorists to help us here, and they've been letting us down. There has been nothing. They assured us it was going to be weakly interacting massive particle. It was just a matter of setting up the right equipment, they would find it. So 40 years has gone by. We have no dark matter candidates that are looking, really compelling. So are we looking up the wrong tree? Should we think more about primordial black holes? How much can we rule them out? that's like, chapter 17 in the book, even beyond the cosmological conflict, primordial black holes. Well, they should be doing all kinds of things. They should be accreting, and we should see the accretion debris. They should be lensing. Well, that's a question I think that might not be a bad idea to revisit. And that's another very new area of astrophysics. And then finally, there's an area which I find fascinating and which really hasn't gotten a lot of press or as much coverage that it deserves, and that is kind of the rebirth of stellar astronomy. That's what astronomy was about, stars. Well, I've hardly mentioned stars in the whole, hour that I've been speaking, but we're learning an incredible amount about how stars work by looking at their normal modes of vibrations. Not just the sun, which has taught us a huge amount, but now other stars in the universe as well. We can peer into their interiors and test our ideas of things like understanding the fluid dynamics of convection. Is the internal structure of the star consistent with the way we think it should be aging? These are questions that now can be asked, and that I would anticipate in the next 10 to 20 years, we're going to make real progress with. So there are a number of different fields which I think are very exciting, and which young people who are in their late teens and 20s now, their universe will be sort of as different in 30 years as it was for me when I look at the universe in 1980 that I understood as a student versus the universe in 2020 that I now see toward the end of my career.
Excellent. Okay, let's since we've been kind of over the past year or two been flipping a lot of classrooms, let's see if I can flip it now. Is there any question, Professor Balbus, you want to ask these students?
Oh, now that's one that I haven't anticipated. Yeah, so I have I have a question. All of you, I guess, are interested, obviously, in astronomy and astrophysics. And so I would be curious to know if that has been something that was an interest in you since you were a little child, or something that developed after you went to school and had an exposure to a good science teacher. How did you get interested in astronomy, at the young age that you have?
Okay, I see some cautious hands up. If you want to answer, feel free to raise your hand. I'll give the floor to Keisha first.
I guess I started being interested in astronomy when I first saw a random book. And it's not a random book, it's like about the Cosmos show, like the one the one that's hosted by Dr. Neil Tyson. And so they put it into a book, and then I read the book when I was like in primary school, and I got interested. And
so then you were in primary school already, and you were able to enjoy it even at that level. That's very good. Yeah. Yeah,
I don't understand the full thing, although now I do. At that time, and then I joined some sort of online course in astronomy that's just self-learning stuff. So I think it like started my interest in astronomy, and it makes me certainly quite passionate about a career considering this path. Yeah, so that's
an interesting and very good answer. That Neil Tyson's program had such a powerful effect. That's exactly what it was supposed to do. So I'm very gratified to hear that. Yeah.
And Carl Sagan too.
Carl Sagan before him. Yeah.
Yeah, he can be my idol. Yes, that one.
Thank you.
Let me share mine as well. So for me, I was fascinated with anything in primary school, with anything to do with planets, stars. So look up, go to the library and take all the books with the pretty pictures. Didn't understand much more than that, but for me it kind of waned throughout early high school, because we still weren't equipped with the right knowledge to really kind of get a new understanding. I think it's really more towards the end of high school when things kind of got back up, when we learned some of the other more deeper physics. And then and then at university, I think that's really where I recall kind of my early fascination, and then kind of said, okay, now I have the ability to study them, to understand them, and then that's how I rolled into it. So for me, it was a little bit of a double peak.
Well put.
So Sonia.
I'm back. Well, I think Zoom doesn't think that my story is interesting, so it decided to cut me off. Okay, so I'll continue my sharing. So what was the last part that I?
No, you were just introducing it. You'd hardly gotten into any detail at all.
Okay. So what I was saying is, at first I really hated astronomy. And then it was because when I was still a high school student, and my teacher forced me to take part in a science competition.
That you weren't interested in astronomy. I mean, but to hate it, that's
I hate it a lot. And then it's I think it's the field that I hate the most in science. And then because I feel that there's too much information, and I need to memorize, let's say, the mass of the Mercury and which planet is having a atmosphere and how do they.
I understand why that wasn't attractive. Okay, yeah.
So and then somehow, and I feel that like this is something that I hate, so I need to overcome it and I need to excel it. And then I try to read more books. And then when I was in Form 5, that is like the very later stage of my high school studies, I came across gravitational waves. And then I also attended a talk by Johnny in COHK. And then that's how I started to get.
All right, well then you don't have to say any more.
General relativity.
After that, all right. Makes perfect sense now. No, but it's interesting that what you have to say about how initially astronomy put you off, because it seemed to be a collection of facts, and Mercury has this orbit and this eccentricity, and the density of Mercury is this, and Jupiter has 12 moons, and so on and so forth. And yes, I can see that, you know, there are some sort of sciences that feel like that, and if they're not presented in some kind of a cohesive way, you know, that can put you off. And to this day, I can tell you, certainly since this is being recorded, I won't mention any names, but I sit in some astronomy talks, and it's exactly like what you're describing to me. It's kind of one slide after another, and this galaxy does this, and this galaxy does that, and then in this galaxy you do that. And you want to say, what am I doing here? You know, I need to have some kind of a coherent picture. And certainly it's the case that the best of astronomers and the best of astrophysics people use the gathering of data as a means to an end. It's not the science itself. And so in some ways you have good taste. You like the good stuff, and you understand that all the numbers, that's not astronomy. That's putting together the science of astronomy.
Very good, very good. Okay, I think we're running towards the end of this session.
Yes.
I would just like to ask Professor Balbus for any closing remarks, maybe things, wisdoms that he wants to impart on you, things that he now knows that he should have told himself when he was about your age. Just any closing remarks.
Oh, yes, I would say what I'm going to say has certainly been said before, but, you know, at this point, I really, can appreciate it looking back on my career. So I would say, first of all, I think all of you, the timing of your birth in terms of a career in astronomy couldn't have been better, because this is really a golden age of new developments, that new instruments and new technologies are allowing to move forward. Things like gravitational wave detectors, things we haven't talked about, things like machine learning techniques, the way that patterns are going to be able to be elicited from complex data. This is all coming up in the next couple of decades, which will be the prime of your careers. My advice, I think certainly for me, the best work that I have done has always been on problems where it is just a fascination at the personal level. In the 1970s, when I was an undergraduate, I was discouraged from going into physics because there were just no jobs. And maybe that was sensible advice, but I didn't take it because that is what I wanted to do. And I thought, well, if there's no jobs, I can at least, it's a little bit like being a professional athlete. You get to be a football player for some period of your life. You can't do it forever, but it's what you love doing, so that's what you want to do. And so that was very much my attitude. And that worked out well. And in particular, I have never regretted pursuing something that I was fascinated by at the scientific and intellectual level. I never looked back and said, well, I wish I hadn't done that. This was a better field to have gotten into. Almost everything, that I've done, which has been a problem which has drawn my attention, has advanced my career. It hasn't sidetracked it. And I think that's a very important lesson. That's where you're going to do your best work. It has to be kind of like falling in love. It's an all-consuming kind of emotional process. And that is where the best science will be done. And fortunately, as I think you can see in sort of the hour that we've had to discuss, you have many different avenues, many different paths that you can fall in love with. And that is the best way that I know to come up with first-class science. You really do have to be completely devoted to what you're doing and not thinking strategically, how should I position myself for here or there. Just go where your heart takes you.
I think this is a very excellent note to start closing out. Before I really end the session, I would like to remind all the participants to also keep an eye out for the Hong Kong Laureate Forum website for more upcoming pre-forum events and also on the updates on the inaugural forum in November 2022. Okay, with that, thank you very much everyone for coming. Thank you, Professor Balbus. Thank you for all the students, for all the questions. I think this has been tremendously fruitful, inspiring, at least it was for me.
Oh, I've enjoyed myself enormously, and I really loved the questions. It was a lot of fun to think about. So thank you for both the invitation and to the participants who came. I've really had a great time. I feel very uplifted now. So thank you for that.
Okay, thank you very much, everybody. Bye-bye.